Hi there, Mrs. Lemke here. Now that we are fully aware that a log is an exponent, it should make a lot of sense as we look at these properties of logarithms that exponent properties and logarithm properties are pretty much the same property because, as I said, a logarithm is an exponent. So remember that, this is just a little side note over here, recall that if we do not write a little subscript base, the default base is base 10. So if we just write log, it means log base 10. All right, so these are just written kind of generically, but understand that it would apply even if the base was something other than 10, doesn't matter. So when we're multiplying like this, right, I have two things with the same base here, base x, and two exponents, we actually add those exponents together. So similarly, if I have a logarithm and my logarithm has a product with it, so I'm taking the log of a product, I could similarly add those. Do you see the connection here? So this multiplication sign in my property becoming an addition sign is really the same as what happens with the logs. All right, so with division, if you have the same base, you can subtract the exponents. So here with division, I would subtract my logs because logs are exponents. And if I have a power to a power, at least that's what I always call this property, a power to a power. I think that's what it was called back, in 1986 when I learned this. You would multiply those. So similarly, we can multiply this kind of power and this kind of power, right? A log is a power to the b is a power. Those could be multiplied. Now, sometimes I refer to this last property as down in front, right? That's what you say to say my father-in-law, Jack Lemke, when he is standing in your way and you're trying to watch the Packer game, you're like, hey, dude, down in front. So you take that exponent that's up there, bring it down in the front and multiply it, okay? That had nothing to do with the Packers. I was just doing that to, kind of jab at the Bears fans out there. Okay, so our zero property, right, is right here. So x to the 0 is 1 as long as it's not 0 to the 0. That's an indeterminate form. Just keeping it legal, guys. And then here, the similar property written with log notation is the following. So remember, a log is an exponent. The is this equal sign. So log is exponent. That was the exponent, right? So no matter what that base is, if I have a log base anything of 1, that's going to be 0. And x to the first is just x. So similarly, this is asking for an exponent, remember? So what exponent goes on a b to make b? B to the blank makes b. That's 1, dudes, okay? So I'd fill in a 1 here, and that's why that's equivalent to 1. Okay, so those properties hopefully seem logical or at least familiar. With the properties back here, like if you get confused, you can always write out examples, right? Like if you're not sure of this property, write that out and say, well, that's x squared 3 times, right? Things like this. Okay, two other important properties, exponentiation and a log are opposites, are inverses. So if I have both, they cancel out. So if I have b to, like on this one, if I have b to a power and I also have log base b, those are opposites. That's exactly the same idea here, it's just the opposite order. If I have log base b and b to a power, okay, this is like two separate ideas. I wasn't trying to make a math thing there, okay? So if I have these two things, this thing and this thing, okay, not trying to write them connected. If I have both of those things, right, those are opposites, those are inverses, they're going to undo each other. And we'll talk about that more going forward. All right, so you may remember from your algebra class, there is a number that is denoted with the letter E. It is in honor of a mathematician whose name started with E. You do not say that Euler unless you want me to seek you out and want to punch you or something. That's Euler, okay, you pronounce it that way. So Euler was a very famous mathematician. His name is scattered all over mathematics for different things that he figured out, and one of them was this number, which is an irrational number. And so you know another irrational number called pi. So it's not super weird that we're using a letter here. Pi is a letter in the Greek alphabet. Just happens that E is a letter in our alphabet. So maybe it seems a little different, but it honestly is not. And so E is the base of what we call the natural log. And it's a base that comes up in a lot of applications of exponents and logs. So on your calculator, if you do second and the division sign, you get this E, okay? And there it is rounded off because it does go on forever and it does not repeat. In spite of all those 1s and 8s, it does not repeat, I promise you. It also is located down here. So you might have noticed or remembered from algebra that there's a log base 10 key, and above that is 10 to the x. This is what we call the natural log key, and it has e to the x up above it, okay? So with that in mind, let's take a closer look. Our e to the x function looks like this, okay? So in order to graph this, first of all, I know that it is an exponential growth shape, and this is what exponential growth looks like. It kind of hugs a horizontal asymptote. In this case, the horizontal asymptote is the x-axis, and then it comes off of that and grows very, very quickly going to the right. So to get values of that, we could use a calculator here, and I could get rid of this stuff from stats class. And here we would have second, and then type this ln key to get e to the, and then type x, okay? And just use the standard window, and you'll get a nicer picture of what I tried to draw there. And if you need some values, you can go to your table and pick off some points that would be nice enough for you to plot. So if we go down here a little bit, we'll get some nice smaller values, right? 0, 1, that's not surprising. E to the 0 would be 1, because anything to the 0 is 1 as long as it's not 0 to the 0. If I have a 1, e to the 1 is, well, this is a decimal for e, right? So there are some nice values in here that we can actually plot, but you can see how it gets really big really fast. That is what exponential growth does, okay? So this is my picture. You can see that it lives entirely in quadrants 1 and 2. So this will be a parent function for a lot of different exponential functions we will take a look at. Now, because because E comes up a lot, we actually use something called the natural log, okay? So if you take a look, I'm kind of regretting that I already filled this out. I think I'm going to erase this even though it's written there, because I feel like you're going to understand better if I just walk you through it, okay? I know this is weird. You know, we've been together for a while. You guys know that I'm a little weird. All right, so if we have our exponential growth function right here, okay, I want to isolate the x, let's say. So to solve for x, I want to take a log and use a log property. So I'm going to use log base e, because I can see that the base part of my exponential function here is an e. And then I'm going to use that property. Remember I talked about saying to my father-in-law, get down in front, Jack Lemke. Okay, and then over here, samesies, didn't change anything. Okay, just used a log property going from blue to green. And then remember that if I have this, right, like we talked about before, if you have log base b of b, that's 1. So this right-hand side is just x times 1. So I'm just going to cross that out because multiplying by 1 doesn't matter. All right, then I have x equals log base e is used so often that it gets to have its own symbol. So log base e of y, we're going to replace this part with its own symbol, and it's the letters ln, and it's read natural log. I think, if I remember right, it's because John Napier is the mathematician who came up with this, and I believe he's a German speaker. That might not be right. I might be spreading lies, but it has something to do with the fact of word order in a different language is why those letters are backwards, right? We read it natural log, but the abbreviation is LN, okay? So all LN means is that it's a log base E, okay? So all of the properties that we discussed earlier that would be true for other bases are true here. Natural log of 1 is 0. Natural log and e to a power cancel each other out, which is what you see for these two right in here, right? Those e to a power, right? This is the thing that I had those bubbles around before. E to the thing and natural log these two. If you have both of them, like you do here and here, they cancel each other out because being inverses. If you remember that natural log means base e, right? Log base e of e is going to be 1, right? And that's what this is saying. And then at the bottom, I didn't finish this one yet. So if I have natural log of x equals, very important mathematical symbol, natural log of y, justice in the universe implies that this, x has to be y, right? And I know that some of you are going to want to say, like, I'm crossing these out. And that's not exactly like good math, but I just think like equal means equal. And so if two parts are the same and you have an equal sign, then the other two parts kind of have to match, right? Otherwise that equal sign couldn't be there. All right, let's take a look at some problems that I'm going to ask that you try some, okay? So we'll do a little together and then you're going to do a little on your own, that kind of thing, okay? So the first few say rewrite the natural log expression as an exponential. So remember that this natural log as a symbol really means log base e. Now, could you write that? Yeah, I mean, you won't, right? As you go forward, you'll like know this. But if you need it as a little crutch for a couple days, we get that. And so this is my base. This is my exponent because a log is an exponent, right? That's the exponent. So what I want to write here is e to the 1 point blah, blah, blah is approximately equal to 4. And I said approximately equal to because of all those dot, dot, dots. Okay. I'm going to come down and do number 3, and then I'm going to have you guys try 2 and 4. So question number 3 says rewrite the exponential as a log. Well, the base part here is an e, so I'm going to use log base e. And then I need to think about what these two things are. Well, my log is an exponent, so I'll put the exponent here, and I'll put this other number in here. Oh, I really did not plan ahead on my spacing there. Were you kind of laughing at me? Yeah, I don't blame you. Yeah, that was not really thinking ahead. Right? Okay, so I want you to pause the video for a second, try 2 and 4, and come back to check. Okay, this is what you should have written for 2 and for 4. Okay, let's move on to some more. All right, the last thing we need to discuss today is expanding and contracting. So these two skills are where you make use of all the different log properties that we have, okay? So in these questions, we have some expressions that are fairly condensed, and we want to spread them out. This is used in calculus a lot because it's going to be easier to operate on things that have little itty bitty pieces, even if you have a lot of pieces, than to operate on something that's one big chunk. And all of these are kind of like one big chunk, okay? So I'll show you what I mean. So for this first guy, I can see here that I have multiplication. I can also see I have an exponent. So I'm going to spread this out. First, remembering that addition of exponents can be rewritten with addition. Did I just say that right? Multiplication of exponents can be rewritten with addition is what I was trying to say. Okay, and then this exponent, I can down in front that. And you see, just like look at it visually, see how much wider this is, and this was all like as one little chunk. That's what we mean by expand. Expand it, okay? Let's do number 4 together. Okay, so a square root can also be written as to the 1/2 power. And I'm going to do that because I know there's a property of logs that lets me do down and front. And then I have multiplication. Okay, and so now I'm going to rewrite this. My multiplication property lets me rewrite this as addition. Okay, so you might want to think about why this 2 ended up just in front of this, whereas this 1/2 ended up in front of the whole shebang. Right, the 1/2, the square root applied to this entire expression x times r. So the 1/2 is with all of this, right? I could distribute that if I wanted, right? Write 1/2 twice instead of having brackets. Whereas over here, that square only was on the 2. It was not on the y. Okay? All right, number 2 and number 3, I'm going to leave for now, okay? And we'll come back and talk about them in a second. All right, condensing is going the other direction, okay? It's taking something that's really spread out and making it into that big chunk, okay? So let's try number 3 together. So in number 3, I see a little down in front that I can undo. And this is like hidden down in front, because really I want to think about that as if it were this, with the 1/5 in the front, and then that can come up, okay? So this is just a little thought bubble. That's not a full step. Okay, so my first full step is going to be this, base 6 log of w cubed, base 6 log of t to the 4th, and base 5 log of r to the 1/5. So there's different bases here. Can I use the properties and smush things together? Well, only if I have the same base. So these two can go together. So base 6 log of, okay, now with subtraction, that's division. So I use division here. And over here, I could choose to rewrite this as the 5th root of r, but that's all I can really do in terms of condensing unless these bases were actually the same, which they are not, okay? So that's the idea of condensing. What I'd like to do now is to have you go back and do those other 2 expansion questions and then do the condensing questions, and then you can take a look at the answers for those because I'll show them on the screen. There also is a PDF of these notes posted for you on your class site. Okay, so pause the video and do those last few to see if you understand, okay? Go back and do the other 2, expand, and then come back and check the rest of the condense. Okay, here are solutions for 2 and 3 in the expand section. Over here, if you just kept this as the base 3 log of 3, that would be okay, but hopefully you do recognize that that is the number 1. In the condensed part, the other 3 solutions are shown here. If I move this record box somewhere. So you can see how you did. Remember that the idea of the condense is to try to get it down as tight as you can to a single logarithm if possible. And all of these you could get to a single logarithm if you kind of fought through it. All right. If you have questions, make sure to talk with your teacher. Thank you so much.